Hi everyone, this is Mr. Hall, and this is a really quick video on the electrolysis of aqueous solutions. It's a slightly different bit of content to what we've done previously with molten ionic compounds. It's a bit harder. There's a few extra rules you need to know, so you have to be very aware of those things. So there's basically three different things I really want to cover today. The first thing is to identify the ions in ionic solutions. It's pretty straightforward compared to what you've done before, but with a couple of extra caveats. We're also going to work out or deduce what is produced at the anode based on the nature of the anion, and we're also going to deduce or work out what's produced at the cathode based on the reactivity of your cation. All right, so let's just review what we've done previously. Now, previously, when we learned about electrolysis, we learned that there are two ways in which you can split up the ions. Okay, now what we've done before is basically we can melt the ionic substance, and that's pretty straightforward because you've only got two different types of ion to contend with. And it works. The only problem is that for most ionic substances, they have melting points in the thousands of degrees Celsius. So you need loads of energy to melt them and to do this process because it needs electricity as well. It works. It's just not an economically attractive option if you're an industrialist. So what you instead do is you can dissolve it. Now, dissolving is great because you don't need as much energy. However, you do have a couple of issues with this, namely the fact that you have more than two ions in that solution, and that's what you have to contend with. So when you have an ionic compound dissolved in water, the thing you have to remember is that water naturally dissociates, and it dissociates into H+ or hydrogen ions, and you have hydroxide ions, which are OH-. The H+, if you remember from previous learning, is the acidic part, and the OH- is your alkaline or basic part. So you have those two naturally there anyway. Now, as soon as you add an ionic solution to it, and they get poured into solution, you've then got four different ions. You've got two from the ionic substance and two from water. So for sodium chloride, for example, it will look like this on the picture. You'll have Na+, which is the red circle, Cl-, which is the blue circle, and they were from NaCl. You've also got H+, which are kind of the light red or pink circles, and you've also got OH-, which are the grey circles. So you have four different ions. Now, when I put that as part of an electrolytic cell, like connect it with a battery or so forth, it looks a little bit like this. And when I turn it on, the ions will go those particular directions. So now the question is, which ions will gain or lose electrons and get discharged, i.e. produced, and which of those ions will stay in solution? That's the question. And that's what we have to work out. So let's start with the cathode. Now with the cathode, you've got two different ions here. You've got the H+ and you've got the Na+. The rule here is all governed by the reactivity of your metal in relation to hydrogen. If your metal is more reactive than hydrogen, you make hydrogen gas. However, if your metal is less reactive than hydrogen, you make the metal. Now, in this case, we have sodium. Now, sodium is more reactive than hydrogen, or if you want to put it a different way, hydrogen is less reactive than the metal. As a result, you're going to make hydrogen gas. So the hydrogen ions are going to gain electrons like so. They'll then pair up to form a H2, to form a covalent bond, and that gets discharged. Okay, and the half equations there at the bottom. I'll talk more about half equations in a future video. You can test for the hydrogen gas by doing a pop test. You can collect it in the test tube and do a pop test. Those sodium ions will just stay in solution. Okay, so that's what happens at your cathode. Now at your anode, it's a slightly different story. Okay, so what you've got here is you've got OH- ions or hydroxide ions, and you've got the chloride ions as well. Now the rule here is governed by the nature of your negative ion or your anion. If your negative anion is a halogen, i.e. in group 7, then you're going to make that as a gas or as a molecule, okay? Now, if you look over here, we've got Cl-. It's a halogen, so we're going to make that, and that's going to be discharged. So they're going to donate their extra electrons, which they had, and that goes round to the negative electrode, and they will pair up to form diatomic molecules of gas, and then they will be discharged. And you can test for it, right? So what you could do is you can get some litmus paper, it will probably bleach it white, and that'll be evidence that you've got chlorine gas. The half equation there is at the bottom. Again, I'll cover that in a future video because it's quite complicated. The OH ions you have here, they stay in solution. Now let's look at a different situation at the anode. Let's say that we didn't have halogen, we had something different, like a nitrate ion. What would happen now? Now, because it's not a halogen, you're not going to have this produced. So the NO3-, the nitrite ions, they're going to stay in solution. They will not be discharged. So what happens with the OH- ions or the hydroxide ions? They're slightly different with those. That will be produced, but instead of producing some weird product on their own, they're going to produce oxygen gas in the following way. So they're going to discharge their electrons, like so, and then they'll sort of split up to form two molecules of water, one molecule of oxygen, and that gets discharged. And you can test for that oxygen gas by collecting it, and it can relight a glowing splint. So again, you can prove that these gases are present. Now the half equation there's at the bottom, and if you sort of rewind the video and watch the kind of movement of the atoms and electrons closely, you can actually see that it makes sense. Again, it's something which I'll cover more in a future video. So I went very quickly through some rules there, so it's probably worth getting this down on paper and just kind of getting it laid out in full. So at the anode, if your anion is a halogen, you make the halogen. If it's not a halogen, you make oxygen instead. At the cathode, if your metal ion is more reactive than hydrogen, then you make hydrogen. If it's less reactive than hydrogen, then you make the metal instead. Now, with all those rules considered, let's now try a couple of examples to see if this actually works. So let's start with copper sulfate. Now, copper sulfate, if we have a look at the equation, it's CuSO4. Now, when you work on problems like this, you may want to kind of draw out the ions in a diagram like this if you really want. In order to kind of help you visualize it, I will. So what you've got here is you've got Cu 2 plus, and you've got SO4 2 minus, and we've also got H plus, and we've also got OH minus. Now, obviously, we'll have millions and millions of these in the solution. I'm not going to draw millions and millions because it's going to be long, but I'll just draw the 4 that you have, okay? So the copper ion is going to go over here, and your hydrogen ion is going to go over here. Your sulfate ion is going to go over there, and your hydroxide ion is going to go over there. So the question is, which one are you going to make at which electrode? So let's start with the positive ions, okay? And we're going to need to use this reactivity series to help us. Now, if we remember, if our metal ion is more reactive than hydrogen, we're going to make hydrogen. If it's less reactive, we make the metal. Now let's have a look at what we've got. Hydrogen's here, and I'm looking for copper, Cu. Now I can see copper is beneath hydrogen. So that means that I'm going to make copper at this electrode, okay? So what you'll literally see is like copper coating it. So it's going to start looking quite orange, and then the hydrogen is going to stay in solution. I'm just going to put a circle around it because we're going to have to come back to that later. Now let's have a look at my anode. At my anode, I've got sulfate ion and I've got hydroxide ion. Now the sulfate ion is not a halogen, so I do not make that. So instead, I've got the OH minus and I make oxygen gas. So I'm just going to write O2. And that will sort of steam off, and you can obviously do a test with the glowing spin to see that it's definitely there. Now, what I've got left in solution is SO4, 2 minus, and H plus. So technically, what they can form, if you think about it, I've got 2H plus, add SO4, 2 minus, and that can form H2SO4. So basically what it means is in that solution, it's going to become quite acidic. So that'll become an acidic solution. The reason why I bring that up is sometimes maybe asked, like, what happens to the pH of the solution? In this case, it would become acidic because of your existence of H plus ions. So that's what you make there. Let's try a second example. Now we've got sodium oxide. Now sodium oxide, let's have a think about the formula. Sodium is Na plus, and oxide is O2 minus. If I do a bit of crisscross just to work out what the formula is, that gives me Na2O. All right, so in solution, I've got Na plus and I've got O2 minus. Ooh. I've also got H plus and OH minus. So let's start pairing these in different directions. So I've got the sodium ion going over here, and I've got the hydrogen ion going over here, and then my oxide ion goes over there, and then my hydroxide ion goes over there. So the question now is, what do I make at these different electrodes? Let's start with this one first of all. So I've got sodium and I've got hydrogen. Now if I look at my reactivity series, hydrogen's here, sodium is way up there, so it's much, much higher than hydrogen. So I can't make the metal because it's not below it. I have to make hydrogen instead. So here I'm going to make hydrogen. Now that's going to kind of, be discharged there, and you can trap it and do the pop test to prove that you have hydrogen, but that's what's going to happen there. Over on this side, I've got O2 minus and OH minus. O2 minus is not a halogen, so I'm not going to make that. I am, however, going to make OH minus, which means that I'm going to have oxygen gas being discharged there, and literally you can trap it and test it and so forth, but that's what you're going to form. You have your Na plus and O2 minus still in solution. So what you have is a sodium oxide solution still remaining there. Not a very effective way of splitting them up. Let's try one more, silver chloride. Now silver chloride is, silver's usually Ag+, and you've got Cl-. So it's pretty straightforward in terms of what the formula is going to be. It's going to be AgCl. So in solution, you've got Ag+, and you've got H+, and you've got OH-, and you've got Cl-. So these two are going to go over there because the oppositely charged the oppositely charged ions and electrodes attract each other. And then you've got Ag+ going over here and H+ going over here. So what we're going to make, let's start with our negative cathode. So I've got silver and I've got hydrogen. Now remember, hydrogen is sort of the benchmark at which we have to look for everything else. So I'm looking for silver, Ag. Now you can see silver is beneath it. So because it's beneath hydrogen, I don't make hydrogen. In this case, I make silver. So what you'll see is a very thin film of silver starting to develop around the electrode. This H+ stays where it is. Let's have a look at the other two. We've got OH- and Cl-. Let's focus on the Cl-. Is it halogen? Yes, it is, because it's in group 7. So I'm definitely going to make that. So here I'm going to make Cl2 gas, which you can test with damp litmus paper to bleach it. The OH- stays in solution. So in terms of what you make as a solution, your H+, in theory, is going to combine with your OH- to form H2O. So what you have is basically just a watery solution. It becomes less concentrated as the electrolysis proceeds. And that's how you do it. So I hope this video has been useful, and best of luck when you're completing questions based on this topic.